All right, guys, welcome back. This is the second part of chapter 13.1, and last time we talked about 13.1, just the definition of graphs. We went over what is a graph, what is a vertex, or if you have many vertices, the edges in the graph, the loop, which is a special edge that basically leads you to the same spot. We talked about degree of a vertex, even vertex, odd vertex, and then we went and tried to represent this town. We did the west coast over here. We did this layout of a building, athletic building, and so now I ask you to do this one here. Uh-oh. All right. So A, B, C, D, E, F, G, H, whoops, I, J. Is that right? A, B, C, D, E, F, G, H, H, okay. Okay. Just make sure I can do my ABCs here. All right. Then. Okay, so A, B, C are pretty much evenly spaced out. D is below B, and E is below C, and F is pretty much right next to E a little bit, and G, so D, E, F, G is right here. H is the last one. And then if you look, I is below the A, so I'm going to put that right here. And J is below the F. And K is below the H. So basically we're just going to make the edges with these streets. So we have Creek Street. We have Brook Avenue right here. We have River. We have Sea. We have water. We have ocean that goes all the way across. We have stream circle that starts at F and it goes up and it curves back down to G. And then we have Spring Boulevard at the bottom. And then, what is that? Palm Street. Is that it? Are we done? What are we missing? Yeah, Lake Street, right? Which is F and J right there. Perfect. All right, so that is pretty straightforward map. This one's a little bit more straightforward than the others because it pretty much matched the picture, okay? With the other ones, they didn't really exactly match for the most part. All right, so let's continue, guys, on the next page. So we have path, circuit, connected, bridge, also disconnected. I almost forgot there. All right. So, you know the structure of a graph. Now we're going to look at the movement through a graph. Remember that the whole point of this is, the purpose of this was to make things more efficient, to spend less time, to travel efficiently, and save money. So, think of this as you moving, let's say, in a neighborhood or whatnot. So here is a path, and the path that you take, so let me say movement is, let me add this phrase, through a graph. Remember, this is a graph theory graph, not the algebra graph. Okay, algebra graph is totally different. So a path is basically, guys, a sequence of adjacent vertices and edges that basically are connecting them, okay? So a path that you walk, okay? So if this is a park, all right, you don't have to go through every single path. Just go down your favorite path, right? So let's say we did A, we started at A, then we went to C, B, and then D. Okay? So that means we're starting here. We're going to C, which means we're going down. We're going to B, which means we're cutting through the middle. And then we're going to D. Okay? So if this is a park, that's your favorite route. You want to go to the middle. It's got some nice scenery. That's not really necessarily the most efficient path to D, right? What would have been a quicker way to get to D? Once you were at C, just go straight across, right? So depending on the situation, if you're talking about, hey, I'm in a rush, I got to get there fast, then you're going to take C to D. But if you're just taking a stroll, then you're going to go up to B, come back down, you know. And so now let's change colors here and let's change colors here and do a different path. A, B, D, D, and C. What does that look like? But don't recommend you trace this in the same color because it's going to look like the same path and it's going to look confusing. So maybe dot it, dash it or something. So starting at A, and we go to B, then we go to D, and then we're going to go to D again. What does that mean? Yeah, we went through the loop. Maybe there's a fountain there or something. Okay? And then from there we go to C, which is this way. Okay? So this is what we call a path. And you're going to be really paying close attention to paths in the future in this section because we're going to be using theorems to try to accomplish certain goals, all right, in these paths. Okay, let's take a look at a circuit. So a circuit is a specific path that begins and ends. Begins and ends at the same vertex. And this kind of makes more sense if you're going through this path because wherever you started, that's probably where your car is, right? And you're going to end up coming back to the same place so you can get in your car and go home. Okay, so a circuit is basically, I'm going to start my journey, and I'm going to come back to the same spot. All right, so an example of that would be A, B, C, and A. So notice that immediately you see the same letter twice, one in the front and one in the back. Without even looking at the path, you know you started at A and you're going to end at A. That's a circuit. Okay? You start at A, so go ahead and do your path yourself. See how you do. So this thing makes a triangle. Go to B, go to C, go back to A. Okay? That's a circuit. That's a circuit. It is a path, but it's a specific path ending at the same place where you began, so we call it also a circuit. Okay? Any questions so far with those two definitions? Okay? Path can be wherever, but a circuit has to come back to where you started, all right? Now we have connected and disconnected, okay? So basically, in reference to two vertices, basically, vertices that connect, right? I mean, it's not that different from the word itself. So if you can connect two vertices, basically it's called connected, right? So that's pretty much everything we've been showing, except, think of let's say A and D over there in the picture. You can't just walk across. All right? There's no path going straight from A to D. You have to go through some other vertices to get to A from D. So you can't be doing this. You can't make up your own path. All right? So those two technically are disconnected. Okay? And disconnected would be obviously the opposite. It's basically any two vertices that can be connected, can't be connected. Cannot. Can versus can't, all right?
You have to know all these definitions with the test.
Of course. Well, sometimes, if you're asking if you're going to get vocab questions, you're going to get a few. But you have to know the vocab to do the problem. So you don't not necessarily test it on it directly, it was tested indirectly. So if I say, hey, name two disconnected, spots, and you don't know what disconnected means, then how are you going to answer, right? So it's definitely indirect. So, all right, let's take a look at these. If I make this, let's say these are two neighborhoods, right? If these are two neighborhoods, can you get from one neighborhood to the other? According to this. Nope, there's no path. Okay? So this is definitely disconnected graph. This is a disconnected graph. But all I have to do is create what's called a bridge. Okay? And now the two neighborhoods are connected. That means you can take that path and get to one neighborhood or the next. But looking at particular vertices, that's the wrong color, sorry. So connected. So A and B are connected, definitely. All right. And there's so many examples, B and D, B and E, etc. Okay? You can get from one to the other directly through a path. But disconnected, so B and E, you can't get there directly. Okay. D and G, you can't get there directly. Okay. F and H. Okay, there are no shortcuts. All right, you can't be walking through people's lawns and all that, jumping the fence, and getting bit by a dog and all that. Okay. But those are just looking at vertices. But if you look at the graphs, this is definitely a connected graph. Okay. Now, what you just saw me do was create a bridge. That's the next vocab word. So BE is a bridge. Why? Because if I remove that BE, then we can't cross. We cannot go to one neighborhood or the next. So basically any edge that, if removed from a connected graph, would create a disconnected graph. Okay? Okay? So right here is a bridge. Okay? BE is a bridge. So that will be a connected graph. Take a look at this example. Okay? So, which edge, if I remove it, it's going to be disconnected. There's going to be a disconnected spot. Look at that. Disconnected. Can't get to that spot. Okay? Put it back. Now we're connected again. So that particular spot, so let's just call it AB. So AB is a bridge. What about BD? Why isn't BD a bridge? Okay, think about it. If I remove BD, let's remove it. Is D disconnected from the graph?
No, because we're connected to C.
Yeah, you can still get there. It's going to take longer, right? You're going to have, instead of going down, you're going to have to go this way and then this way, but you can still get there. All right, so BD would not be considered a bridge. Okay? And same thing with CD. Okay? If you want to get to C, you just go this way, go to D, and everything, you can walk the path. All right? Now, so if you can see a line, if you take it out, you won't be able to get to one point to the next, then that particular line is a bridge, okay? Let's take a look at another example. Which lines or bridges here? The top one is a bridge, right? If you take it out, you won't be able to get to the other points. You're not allowed to change in the middle right here. You can't just stop here and make a left or right. You have to go to the... If you take out this one, and this is going to be disconnected over here. If you take out this one, this is going to be disconnected over here. So what's the conclusion? Very good. All edges are bridges, okay? So that's what we mean by bridge, okay? All right, so enough of theory, and let's go ahead and do some exercises on the next page. So I had you do some of these last time, right? So last time was 2 even, 2 odd, and the answer to that one was there's different answers. So right now, that's 2, 2, 2, 2. 2 paths connecting at each vertice. That's 4 even. So the question was 2 even, 2 odd. So if all you have to do is do this, and now this is 3 and this is 3. 2 even, 2 odd. Okay. I saw someone else do this. So they did this, and then they removed this right there. So now that's 2, 2, 1, 1. that's still meeting the requirement. 2 evens, 2 odds. Okay? Anybody come up with something different last time? Okay. So this one is create a graph with 2 even vertices. 2 even vertices. How would you do that? So first, those are your 2 vertices. Now we got to get those to be even. That means I can have 2 or 4 or 6 or 8, any of those. But why go more complicated? Just keep it at the smallest number, 2. How can we get both of those to have 2 paths connecting to them? Draw a bridge. Okay. Yeah, draw an edge. In this case, we're connecting them, so we can call it a bridge. But that's just 1 and 1. How do I get another one? Add another one. Yeah, just you're going to have to curve it. Okay. So now it's 2 and 2. All right. Or you can do 2 curves. Okay. Create a graph with 8 vertices and 1 bridge. Interesting. Eight vertices and 1 bridge. Over here, how many vertices are in that example? How many total letters in the top example right here? That's 8, right? That's 8 with a bridge. Basically, you can just copy that one, okay? You can copy that one if you want. Or you don't have to make the second one all complicated. You can just do 2 of these. All right? That's 8 vertices and 1 bridge. All right, just connect them. Okay? Or you can connect them at the bottom, doesn't matter. Okay? Or you can connect them this way. It's all the same answer, okay, guys? It looks different, but it's accomplishing the same goal, all right? Okay. Okay, so for these here, it says use the graph to answer questions 7 through 10. All right. So there's our graph right here. Is A, B, D, F, E, C a path? Without even tracing it, is it a path? Even if you just went to A, B, it's a path. Okay? This is just a longer path, but a path is a path, all right? So this is definitely a yes. Now, can we verify that? Sure. Start at A, go to B, go to D, go to F, E, and C. Okay? Again, all you have to do is walk from one place to the next, and you just completed a path. As long as you're just not standing still, hanging out in one spot. Now, so path, that's very general. Circuit is very specific, right? Now, without even tracing it.
No.
How do you know?
Because it doesn't end with an A.
Perfect, perfect. Yeah, it's got to end at the same spot, okay? So it starts at A and it does not end at A. Therefore, immediately, without even tracing the path, you know it's not a circuit. Okay? So let's just verify that very quickly. So A, B, D, F, E, C. Oh, that was the same one. Sorry. Now, all we needed to do to make it a circuit is to complete one more path, right? So go ahead and write the correct circuit sequence for number 9. So it says, give an example. I mean, you can just use this one. Just add that extra letter, right? You got to go from here back to your starting place. Or you can just do some other path. So just add an A, right? Just add an A. That way, it's a circuit. Okay. Is the graph connected or disconnected, guys? Are there any spots that are disconnected? No. So it's connected. So there's no disconnected vertices. Sometimes you'll have one. Okay? A connected graph is shown below. Identify any bridges in the graph below. So think about this, guys. Which edge, if you remove it, will create a section that's disconnected that you wouldn't be able to get to at all?
B to E.
Okay, why is that?
Because if you
Because
move it,
if you remove it, then you wouldn't get to it.
Get to what?
Get to the E.
Yeah. So it's like an island over there, right? So if you take that thing out, you're gonna have to go swimming, okay? So this is a bridge right there. Now what about C and F? CF. Is that a bridge? Okay, so if I take this out, can I get to F?
Yes.
I just gotta go around.
Through the I.
So that is not a bridge. Now, if you take them both out at the same time, but that's not really the definition of a bridge. Okay? It's just one bridge at a time. Okay. So definitely the answer is B and E. CF and GI are not bridges. Okay. Okay, so right in the next page you have all the answers, just in case you were absent or whatever. It's got the first part that we looked at. And then here's some examples for the second part, okay? All right, nice job, guys.